Astronomers tracking 3I Atlas say it has altered its course, worrying scientists about its close proximity to Earth.
A fast-moving object the size of Manhattan is hurtling towards our solar system, and it will make its closest pass to Earth.
The joint NASA and Harvard emergency briefing, hastily convened under tense and extraordinary circumstances, marked one of the most startling astronomical announcements in modern history. The briefing room, usually a controlled environment of scientific precision, pulsed with a rare sense of urgency. Reporters, researchers, and government liaisons filled every seat as the screen behind the panel displayed a single chilling phrase: 3I Atlas, collision course with Mars confirmed. The words hung in the air like a cold shockwave, signaling the first time a confirmed interstellar object was projected to directly impact another planet in the solar system. It wasn't just an astronomical anomaly, it was a cosmic event of staggering proportions, one that carried implications for planetary science, astrophysics, and humanity's understanding of the interstellar frontier. Before we start, please don't forget to like and subscribe to our channel for more updates. 3I Atlas had already been a point of fascination since its discovery. As the third identified interstellar object after Oumuamua and Borisov, it carried with it a sense of mystery. But what made it extraordinary now was not its origin, but its destiny. NASA's Jet Propulsion Laboratory, in collaboration with Harvard's Center for Astrophysics, had been tracking its trajectory for months, refining calculations as it sliced through the solar system at astonishing speed. While initial assessments suggested a near miss of the inner planets, recent data revisions, influenced by gravitational perturbations and subtle non-gravitational forces, showed a horrifying reality. 3I Atlas was on an unavoidable collision course with Mars. The date, while still months away, was now locked into the models with an error margin of less than 0.01%. The implications of this finding were both thrilling and terrifying. Mars, our neighboring world, target of countless robotic missions, and potential future home for humanity, was about to be struck by an object of interstellar origin. The energy release, NASA's scientists explained, would exceed the largest nuclear detonation on Earth by several orders of magnitude. Based on mass and velocity estimates, 3I Atlas was traveling at nearly 85 kilometers per second relative to Mars. That velocity, combined with its estimated mass, roughly the size of a mid-sized mountain, meant the impact would unleash energy comparable to the Chicxulub event that ended the age of the dinosaurs. The red planet, long thought to be dormant and geologically silent, was about to awaken violently. The atmosphere in the briefing turned grave as Harvard astrophysicist Dr. Leona Serrano stepped forward. Her team had been modeling the potential after-effects on Mars's thin atmosphere and terrain. With a solemn tone, she described how the collision would carve a new crater possibly larger than Hellas Planitia, one of the largest impact basins in the solar system. The plume from the impact would eject dust and debris hundreds of kilometers into the Martian sky, potentially creating a temporary global dust shroud. This could lead to temperature drops across the planet's surface, effectively plunging Mars into a kind of brief impact winter. For the array of orbiters and rovers stationed on and around the planet, it was a death sentence. NASA's Perseverance rover, along with the Ingenuity helicopter, would likely be destroyed by shock waves or buried under falling debris. Even the satellites orbiting Mars were not entirely safe. Depending on the trajectory of ejected material, there was a real possibility of orbital contamination. Tiny, high-velocity fragments spreading outward, capable of damaging spacecraft electronics and optics. Dr. Serrano's analysis was followed by Dr. Eli Price of NASA's Planetary Defense Coordination Office. His presence itself was a signal of how seriously the event was being treated. Planetary defense, traditionally concerned with Earth's safety, was now being applied on an interplanetary scale. Price explained that the window for altering 3Y Atlas's course had long closed. Even if every propulsion resource at NASA's disposal were turned toward it, the object's mass and velocity made deflection impossible. Instead, the focus had shifted to observation and data collection. The event, though catastrophic for Mars, represented an unprecedented opportunity for science. For the first time, humanity would witness an interstellar body interacting with a planetary surface. The data gleaned from such an impact could reshape understanding of both planetary geology and interstellar matter. As the cameras focused in, NASA's Director of Operations outlined the response timeline. A series of spacecraft, including existing Martian orbiters and new probes already being fast-tracked under emergency funding, would be repurposed or launched to record every phase of the event. The goal was to capture high-resolution data before, during, and after the impact. Mars' Reconnaissance Orbiter would be positioned to take sequential imaging of the collision site. MAVEN, the atmospheric study probe, would measure the shockwave's propagation through the thin Martian air. Meanwhile, telescopes across Earth and lunar orbit would synchronize their observations to ensure no fragment of the event was missed. In essence, Mars was becoming a natural laboratory for one of the most dramatic physical experiments in cosmic history. A collision of worlds scripted not by humanity, but by the universe itself. Even as the scientific community buzzed with both fear and fascination, there was a deeper undercurrent to the discussion, a philosophical one. Humanity had always gazed at Mars as a mirror for its ambitions, a symbol of exploration and survival. The planet was the centerpiece of future colonization plans, the imagined cradle of a second branch of civilization. Now, that symbol was under existential threat. Would the impact destroy the delicate potential habitats humanity had envisioned? Could underground water deposits or frozen CO2 reservoirs be vaporized, altering Mars's potential for life-supporting chemistry? Harvard astrobiologist Dr. Mei Kobayashi spoke with an intensity that quieted the room. She emphasized that such an event could provide insights into how life, or the ingredients for life, respond to planetary-scale cataclysm. It was a grim experiment, but one that might echo the early days of the solar system when collisions forged the conditions for habitability. As the hours of the briefing unfolded, visual simulations filled the screens, digital projections showing the fiery descent of 3I Atlas through the Martian atmosphere. The object's surface would begin ablating violently, glowing brighter than any meteor previously recorded. For a brief moment, Mars would host a second sun. The impact, according to the models, would occur near the Martian equator, in a region that had long been studied for its potential ancient riverbeds. The chosen impact zone, unintentional as it was, could reveal layers of geological history buried beneath the surface for billions of years. Cameras and spectrometers would aim to capture the light spectrum of the explosion, providing clues about the composition of both the object and the Martian crust. The energy release would melt rock into glass, vaporize kilometers of regolith, and possibly ignite transient plasma phenomena as ionized materials collided with atmospheric particles. NASA's administrators maintained a tone of calm authority, but the undercurrent of unease was palpable. This was not an event they could stop, only witness. The collision of an interstellar traveler with a terrestrial planet was, in cosmic terms, a normal occurrence. Yet for humanity, whose machines and aspirations dotted the Martian landscape, it was a reminder of how fragile those ambitions remained. Dr. Robert Glass, head of orbital dynamics at JPL, summarized it succinctly. We're about to see what happens when the universe reminds us that it doesn't take our plans into account. His words echoed the ancient humility of astronomy, the acknowledgement that even as humanity reaches outward, it remains a small participant in the larger, indifferent drama of celestial mechanics. Harvard's contribution to the analysis brought a more theoretical dimension. Researchers there had been studying 3I Atlas's composition since its discovery, using spectroscopy and reflected light data. The results indicated an unusual chemical makeup, not entirely consistent with any known solar system body. Traces of exotic isotopes suggested that 3I Atlas originated from a distant stellar nursery, possibly ejected during the early formation of another planetary system. That made the upcoming collision more than a planetary event. It was a meeting of worlds separated by light years, a cosmic handshake written in fire and dust. Some of the materials embedded within 3I Atlas could be older than our sun, remnants of long-dead stars. When it struck Mars, those ancient atoms would merge with Martian rock, fusing two stories of cosmic evolution into one violent chapter. NASA and Harvard both emphasized that this was a once-in-a-species opportunity. Despite the destructive nature of the event, It promised data that no simulation or lab experiment could ever replicate. High-energy impacts of this magnitude were common in the early solar system, but had not been directly observed by any human instrument. For planetary scientists, this was akin to watching the past unfold in real time. Every sensor, telescope, and camera available would be turned toward Mars when the time came. Even instruments not designed for impact observation, like the James Webb Space Telescope, would adjust schedules to contribute. The collaboration was international, uniting agencies from around the world under a single purpose: to witness and record one of the rarest events in modern astronomy. The press corps at the briefing pressed for answers about possible ripple effects beyond Mars. Could debris from the collision pose a threat to other planets or even Earth? Dr. Price responded with cautious reassurance. The physics of the event, he explained, confined most debris to the Martian system. The thin atmosphere and Mars's relatively small gravitational field meant that while some material might escape into space, its trajectory would disperse harmlessly. The real concern was the preservation of observational assets and ensuring that any robotic missions in Mars' vicinity were protected or repositioned. NASA's Deep Space Network had already begun transmitting contingency commands to orbiters, preparing them to either shelter in safe orbits or redirect antennas to capture impact telemetry. As news of the briefing spread globally, public fascination reached fever pitch. Social media platforms were inundated with renderings, countdowns, and amateur theories. The collision was dubbed by some the Red Impact, a phrase that quickly trended across platforms. Artists imagined the fiery descent, while scientists struggled to temper speculation with sober facts. Space agencies outside the United States, including ESA and JAXA, released their own statements, confirming independent verification of the collision path. For once, the scientific world spoke in a unified voice. There was no uncertainty left. The cosmos had drawn a line through the solar system's quiet stability, and humanity could only prepare to watch. The Harvard-NASA partnership extended beyond observation logistics. Researchers began planning how to interpret the data that would flood in once the event occurred. Spectroscopic readings from orbit would be analyzed for molecular traces, particularly those indicating organic precursors or hydrated minerals. The violence of the impact would expose deep Martian strata, potentially revealing materials untouched for eons. Harvard's Department of Planetary Chemistry was already constructing models to predict how high-pressure shock conditions might transform Martian minerals into new crystalline structures, or even synthetic compounds previously unknown. This was not only an astronomical event, it was a natural laboratory for high-energy chemistry and geology. The psychological atmosphere within NASA's ranks was one of somber awe. Engineers who had spent years designing and guiding rovers on Mars felt as if they were watching their creations march toward extinction. The Perseverance rover, still dutifully collecting samples, was now part of a doomed mission. Its last transmissions might one day become the most poignant in NASA's archives, a robot bearing silent witness to a planetary apocalypse. In the weeks following the announcement, a growing number of scientists volunteered for the Mars Impact Observation Project, a task force dedicated to ensuring that the event was recorded in the fullest possible detail. The commitment was not just professional, it was deeply emotional. For many, Mars represented the culmination of human exploration, and to see it threatened evoked something primal: the fear of losing a dream. Meanwhile, astrophysicists debated the origins of 3I Atlas with renewed vigor. If its composition truly differed from local celestial bodies, it could provide clues about planetary systems beyond our own. The collision might seed Mars with new materials, altering its elemental balance. In an ironic twist, some speculated that the impact could create transient conditions conducive to chemistry resembling prebiotic reactions. The energy of the explosion, the presence of water ice, and the introduction of exotic compounds could briefly replicate the violent conditions that once sparked life on Earth. It was a poetic possibility, destruction giving birth to potential creation, even if only momentarily. NASA's Communications Division also addressed the impact's visual observability from Earth. Due to the timing and geometry of Mars's position relative to the Sun, the event would be visible through high-powered telescopes as a bright flash followed by a lingering atmospheric plume. For the first time, ordinary people with access to modest telescopic equipment might witness an interplanetary collision. Observatories across the globe began planning synchronized observation schedules. Amateur astronomers were urged to participate, their data to be included in a global mosaic of visual records. The sky, for a brief instant, would tell a story millions of kilometers away, uniting observers under the shared wonder of a cosmic collision. In the halls of Harvard, discussions turned to deeper implications. Philosophers of science and cosmologists joined the debate, contemplating what it meant for humanity to bear witness to such an event. The universe, they noted, had no preference for creation over destruction. Both were parts of the same endless process. Mars, so often depicted as humanity's next home, was now a reminder of the raw unpredictability of the cosmos. The collision reinforced a truth long known but rarely felt so viscerally, that all planetary bodies, no matter how stable they appear, exist in a precarious balance amid forces far beyond control. Even as technology expands human reach, the laws of celestial motion remain indifferent to ambition. Amid the intellectual intensity, practical challenges pressed forward. Engineers at NASA began recalibrating orbiters to minimize risk. The Mars Atmosphere and Volatile Evolution MAVEN mission adjusted its orbital parameters to ensure it could survive long enough to transmit atmospheric readings post-impact. The European Space Agency coordinated with NASA to reorient the trace gas orbiter, which would attempt to capture high-resolution imagery of the impact site once dust began to settle. On Earth, massive computational resources were allocated to simulate potential outcomes of the impact, from crater morphology to seismic propagation through the Martian crust. Every detail mattered, not just for curiosity, but for the safety and future of planetary exploration. The intensity of the emergency briefing underscored another sobering reality. Humanity was still a novice in cosmic defense. Despite years of progress tracking near-Earth objects, the interstellar nature of 3I Atlas had caught systems off guard. It had approached from a trajectory that defied conventional early detection methods. The event sparked discussions about the need for deeper space monitoring systems, arrays capable of detecting interstellar objects far before they entered the solar system's inner regions. The collaboration between NASA and Harvard symbolized a new urgency in this frontier, the understanding that the solar system is not an isolated sanctuary, but an open crossroads through which objects from distant stars may pass at any time. The media's coverage transformed the collision into a cultural moment. Documentaries, special reports, and even cinematic visualizations appeared within days of the briefing. Yet beyond the spectacle, scientists continued their sober work. The countdown to impact was being refined daily, with new measurements confirming the precision of the predicted date. Each update added both clarity and tension. It was the paradox of science at its most human, detached in its pursuit of truth, yet deeply affected by the enormity of what it studied. For researchers, the coming months were to be filled with sleepless nights, final calibrations, and the weight of witnessing something that no previous generation had ever seen. The countdown to impact had already begun to reshape the world's scientific landscape. Laboratories that had once worked in isolation now found themselves aligned toward a single purpose: decoding every last secret of 3I Atlas before it met its fiery end on the Martian surface. Across NASA's facilities, teams of engineers, astronomers, and physicists operated in 24-hour shifts. There was a shared sense that history was unfolding in real time, that each dataset gathered before the collision was a precious fragment of knowledge that might never again be available. The object itself, still distant but swiftly approaching, had become the most studied body in the solar system. Every telescope capable of tracking it was doing so, from the deep space observatories in Chile's Atacama Desert to the ice-shielded domes of Antarctica. Even radio telescopes, usually reserved for deep space signals, were reconfigured to detect the faint emissions and reflective anomalies that might reveal something new about its composition. Within the Jet Propulsion Laboratory, a specialized task group had been assembled under the name Vigilant Array. Their mission was not to prevent the impact, such an endeavor was impossible, but to ensure that humanity understood it in the most intimate detail imaginable. They worked under enormous pressure, balancing the physics of orbital mechanics with the delicate limitations of existing infrastructure. Every instrument that could be spared from other missions was repurposed. Unused satellites, dormant probes, and even small CubeSats left idle in Earth's orbit were given new coordinates to capture the event from unique angles. It was an improvisational dance of science and engineering, driven by the certainty that there would be no second chance. For planetary scientists, the event represented an unprecedented opportunity to test long-standing theories about impact dynamics. The Chicxulub impact that had transformed Earth 66 million years ago had always been a matter of geological deduction. This time, the process would be recorded in real time, with data streaming in from multiple vantage points. Dr. Rhea Morgan, a dynamicist from the University of Colorado, explained in one briefing that this event could confirm or refute half a century of modeling about high-velocity collisions in low-atmosphere environments. The thin Martian air meant that the atmospheric entry would be less impeded than on Earth, allowing the object to retain nearly its full velocity before striking the surface. The result would be a near-perfect high-energy impact scenario, one that scientists had simulated but never truly observed. In addition to the physical and geological implications, the event had begun to stir deep conversations within astrobiology. Mars had long been suspected of harboring subsurface microbial life, or at least remnants of it, and 3I Atlas threatened to radically alter those conditions. Some scientists proposed that the shock waves could expose previously inaccessible aquifers, while others warned that the sterilizing heat would destroy any remaining biosignatures. The debate was fierce, and it cut to the core of humanity's fascination with the red planet. Would this interstellar collision extinguish potential traces of Martian life, or would it paradoxically reveal them? No one knew, but the possibility electrified the field. Instruments on orbiters and telescopes were being recalibrated to look specifically for chemical changes that might hint at the sudden release of organic compounds. Even as the scientific community pushed forward with methodical rigor, the human dimension of the crisis deepened. Space exploration had always been a symbol of unity and progress, a domain where the best of human curiosity met the vastness of the unknown. Now, that ideal was being tested. Public reactions ranged from awe to anxiety. Artists painted visions of Mars igniting in the night sky, while philosophers wrote about cosmic fate and the fragility of existence. The event became a mirror reflecting humanity's emotional spectrum, its wonder, its fear, its yearning to find meaning in the movements of celestial bodies. Religious leaders in various traditions interpreted the impact as a reminder of divine power or cosmic cycles. Astrologers, often dismissed by the scientific establishment, found their charts suddenly in high demand as people sought symbolic understanding of what it meant for another planet to be struck down by a wanderer from the stars. Meanwhile, the interagency collaboration expanded beyond academic institutions. The Pentagon, the European Space Agency, and the United Nations Office for Outer Space Affairs all entered the conversation. Though the event posed no direct threat to Earth, its implications for planetary defense were immense. Simulations demonstrated that if such an object had been aimed even fractionally differently, it could have become an extinction-level threat to our own planet. The idea that an interstellar projectile could arrive with little warning was deeply unsettling. Governments quietly accelerated funding for early warning telescopes and long-range radar systems designed to detect objects on non-solar trajectories. The world's military satellites, typically used for terrestrial surveillance, were temporarily repurposed to track 3I Atlas in its final approach. For the first time, defense and science stood side by side, not in opposition, but in shared vigilance. At Harvard, a different kind of energy filled the halls. The Department of Astronomy had transformed into a nerve center of theoretical modeling. Graduate students and veteran physicists alike worked feverishly to understand how interstellar radiation and cosmic dust might have altered 3I Atlas during its long journey between stars. Every fragment of its light spectrum was dissected for hints of rare elements, isotopes, and crystalline structures. Some data hinted at the presence of materials that had never been found in our solar system, complex silicates and exotic metals that seemed to form only in the environments of supernovae. If confirmed, this would mean that when the impact occurred, Mars would be dusted with matter from a star that exploded billions of years ago. It was a poetic thought. A planet once thought dead would soon be touched by the remnants of a stellar birth long past. NASA's media division began releasing composite imagery of 3Y, Atlas's approach to maintain public transparency. The object appeared irregular and rugged, spinning slowly as it hurtled through the void. Its coloration was unlike that of ordinary asteroids. A deep bluish hue, perhaps from surface crystallization or ionized metals. The press dubbed it the Azure Wanderer, a name that captured both its beauty and its otherworldliness. Images of it adorned magazines, posters, and digital feeds, reminding everyone of the inevitable impact to come. Despite its destructive trajectory, people could not help but marvel at its elegance. The paradox was striking. The same object that promised devastation for Mars inspired an outpouring of fascination and even affection among the public. In universities across the world, professors adapted their lectures to include real-time updates about the event. Students who had once studied impact mechanics in the abstract now had a living example unfolding in their lifetime. Science classrooms buzzed with excitement as young minds imagined the possibilities of what new knowledge might emerge. For many aspiring astronomers, this event became a formative moment, one that would define their future careers. Governments noticed the surge in interest in the sciences and began pouring additional funds into research education programs, hoping to channel that collective curiosity into innovation. The cosmos had always been a source of inspiration, but never before had it so directly united academia, politics, and the public. Behind the scenes, however, tension brewed. The logistics of observing the impact were enormously complex. The timing of Mars's orbit meant that only certain windows would allow clear visual data from Earth-based observatories. Moreover, some of NASA's assets were nearing the end of their operational lifespans, raising concerns about whether they would survive long enough to record the event. Engineers debated whether to risk altering satellite orbits to gain better vantage points, knowing that a single miscalculation could render them useless. There were discussions about deploying emergency microprobes, tiny, fast-built crafts launched from Earth to provide last-minute telemetry. Each plan carried risk, cost, and uncertainty, but the scientific imperative was overwhelming. No effort seemed too extreme when faced with such a singular opportunity. As 3I Atlas drew closer, the object's influence began to manifest in the environment around Mars. Instruments detected subtle perturbations in the planet's magnetic field and faint dust activity within its exosphere. Some of this was likely the result of gravitational interactions, but there were anomalies that defied simple explanation. One hypothesis proposed that volatile materials sublimating from 3I Atlas were interacting with the Martian magnetosphere, generating temporary auroral phenomena. For a brief moment, Mars appeared to glow faintly at its poles, an ethereal light that captured the imagination of the world. If the data were accurate, it meant that the cosmic visitor was already beginning to change the planet before even touching it. Amid this unfolding drama, attention turned to the human aspect of Mars exploration. Though there were no human missions on the planet, thousands of people had dedicated their lives to preparing for that eventual goal. Engineers at SpaceX, Blue Origin, and other private spaceflight companies followed the developments with both fascination and despair. Their dream of colonizing Mars now faced an unpredictable setback. The impact could destroy key landing sites, erase carefully mapped terrains, and change atmospheric conditions for decades. Yet paradoxically, it might also create new landscapes, fresh craters, molten plains, and mineral exposures that could one day become the focus of new missions. The challenge was immense, but so too was the sense of cosmic perspective. Space was never safe. It was an environment of continual transformation. The dream of reaching Mars, though delayed, had not died. It had merely entered a new chapter. The weeks leading up to the collision saw a crescendo of global engagement. News outlets broadcast countdowns, and observatories held public viewing nights. In major cities, planetariums ran live simulations of the trajectory, drawing record crowds. Humanity, for all its divisions, found rare unity in shared anticipation. Across continents, people looked up at the night sky, knowing that on that tiny red dot, an event of unimaginable power was about to unfold. It was a collective meditation on time, distance, and fragility. The collision would not harm Earth, but it reminded its inhabitants how narrow the line between safety and catastrophe truly was. Scientists at Harvard began publishing theoretical models that suggested 3I Atlas could contain trapped gases or volatiles. If true, the impact might release shock waves not only through solid rock but also through sudden bursts of vaporized material. The resulting plume could rise far higher than expected, possibly extending beyond Mars's escape velocity. That meant fragments of Martian and interstellar material could be ejected into space, eventually drifting toward other planets or even Earth. Though the risk of contamination was minimal, the idea that microscopic fragments of Mars might one day fall on our world as meteorites fascinated researchers. The universe was a closed loop of exchanges, and this impact was one of its grandest acts of redistribution. In the control rooms of NASA's Deep Space Network, preparations reached their final phase. Arrays of massive radio antennas in California, Spain, and Australia were synchronized to record the moment of impact in multiple frequencies. The data would then be triangulated to produce a real-time reconstruction of the event. The level of precision required was staggering. Any delay or misalignment could result in data loss, yet morale remained high. The engineers understood that they were about to participate in one of the greatest observational achievements in the history of science. Some compared it to the first moon landing, an event that would be remembered for generations. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on 3I Atlas heading toward Mars impact? We want to hear from you. Thank you for watching and see you next time.